Session 5 will begin with a review of Shewhart's idea, followed by a description of the origins of the scaling factors. Finally, it outlines some of the differences between how SPC works and the approach taught in courses in statistics. The material covered in this session will use the Understanding SPC text and the SPC workbook.
I'd like to begin this session with a summary of the concepts and computations that we have talked about in the past 4 sessions. When a process is operated in economic equilibrium, all of the causes with dominant effects will be in the set of control factors. We want to control all of those causes that have dominant effects, and we do not seek to control causes with trivial effects. So this is Shewhart's approach to economic operation. When causes with dominant effects remain uncontrolled, a process cannot operate in an economic equilibrium. An uncontrolled but dominant cause is called an assignable cause. So we divide the uncontrolled factors into 2 groups, assignable causes and common causes of routine variation. Now, assignable causes will take the process on walkabout. Here's a process with a CP of 1.46, good potential. But as the assignable causes take the process on walkabout, the operators will, of course, adjust the control factors, trying to stay on target. And as a result, you'll end up with a process whose piece of PK is something like 20% and has 21% scrap. The result, increased scrap, more marginal product. When the process is not operating up to its full potential, the assignable causes are taking it on walkabout. But on target with minimum variation requires that assignable causes be made into controlled inputs. And as we find the assignable causes and make them part of the set of control factors, we reach an economic equilibrium, which means predictable operation, which means minimum variance. So the objective of a process behavior chart is to identify when assignable causes of exceptional variation are present or affecting the process. The running record shows the process performance. 3 sigma limits computed from the data use the common causes of routine variation to define the process potential. These limits approximate what the process can do when it is operated predictably. So a process behavior chart compares the process performance with the process potential. When the running record goes outside the 3 sigma limits, we have evidence that an assignable cause with a dominant effect is present. Economic operation requires that all assignable causes be moved into the set of control factors. Now, we're going to look at an example of how this works. Harry finished the class and went to work on projects there where he worked. This is the second project he tackled after he finished class. He was looking at cooling water temperatures and pressures. And he was just rummaging around to see what he could find out. They had a problem. Their scrap costs were running over $2 million a year in this one department. And so he looked around at what data was available, and in the filing cabinet, he found these old-fashioned circular graphs that recorded the temperature and pressure. So he has these recordings of temperatures and pressures. He decides that he wants to put them on a chart. the chart blank in front of him has 5 blanks. So he picks 5 times throughout the day and takes the temperatures and pressures at those 5 points each day. Now you have these data in the textbook, Understanding SPC, page 53, exercise 3.2. So if you want to play with these data yourself, you can. Now, he had these data out of the filing cabinet. This is a retrospective study. He's actually creating this chart on January 15. He went back to the beginning of December to collect his data. And he had 5 numbers each day. I didn't write all the data down. And then he computed his average and his range for each day. And he used about the first half of the data to compute his limits. So here are the first half of the data as they're shown in the textbook. And the average is 57.88, and the average range is 8.5. So we get upper limit for the averages of about 62.8, a lower limit for the averages of about 53, and an upper limit on the ranges of 18. And everything looks copacetic here. Then he continues to plot his data up until the current time. And we have this. Something happened. When did it shift upward? We look at the dates and we see they're working a 5-day week. And the 21st is Monday of a short week. Now they tell me there are 35 ways to turn the water system on. The cooling water has a chilling unit. It has a cooling tower. There are different fan settings. There are different numbers of pumps. There are different settings on the chilling unit. They said, all in all, we have 35 different configurations we can set this system up in. What do you want to bet? What do you want to bet? The 21st of December, a substitute went down there and just turned on everything. The pressure goes through the roof. Then on Super Monday, January 4, they come back from the Christmas shutdown and somebody turns on a minimal system. Yeah. You see, the water system was invisible. It was down in the basement. The operators couldn't see it. But the water system is being operated unpredictably. Now, why do you think Terry used the first half of his data to compute these limits? Let me ask it differently. What do you think would happen if Terry used all the data to compute the limits? You think the limits might blow up? Let's find out. Using all 24 data in the textbook, we get the limits shown here in black. The upper limit went from, for the averages, went from 62.8 to 62.6. The central line went from 57.8 to 57.2. The lower average limit went from 53 to 51.88. The average range went from 8.5 to 9.3, so the upper range limit went from 18 to 19.6. Yep, those limits got wider. You were expecting more than that, weren't you? The details change when we change our baseline, but the story remains the same. The purpose of a process behavior chart is to characterize the process operation. And while the details change, some points that are just outside one set of limits or just inside the other set of limits, the overall story remains unchanged. This process is being operated unpredictably. We do not have to wait until our process is well behaved to get good limits. We can get good limits from bad data. You see, the computations are robust so that the technique will be sensitive. And we're going to find out why that happens today. Well, what was the impact of this little chart? Well, they had been running about $2 million a year for scrap in this department. So the last month they had over 1% scrap was the month he did this chart. They discovered they had a problem with the water system. Well, that was easy. They put temperature and pressure gauges upstairs on the mixers, so the operators could tell what the water system was doing. When you quit handicapping the operators, they did a lot better. In fact, the scrap rate went down to 2/3 of 1% over the next year. And the foreman said, we found some other problems with our equipment, and by middle of model year 4, we were running 0.2% scrap. Over 2 million a year saved by simply ceasing to burn the toast.
For the origin of the scaling factors, we return to the SPC workbook, page 23.
Now, we saw page 23 yesterday afternoon. We talked about the empirical rule. Now I want to talk about the other of the two steps that go into the scaling factors. And that's using the summary statistics to estimate the process parameters. And that is explained at beginning at the bottom. This is a distinction that if you fail to make it can lead to all kinds of confusion. We work with statistics. Statistics are values calculated from the data. There are things like averages, ranges, medians, root mean squared deviations, standard deviation statistics, all the typical computations you learn in your baby course in statistics. Data plus arithmetic equals statistic. So the convention in most books, we use Roman letters for statistics, X bar, X tilde for the average or median, R bar for the, or R for the range, and so on. On the other hand, parameters are unknown descriptive constants for the characterizations of a predictable process for the distribution of X. So here on page 23 in the workbook, the mean of the distribution for X and the standard deviation for the distribution of X, and the convention here is Greek letters, mu and sigma. Now, I found that people are really not up to date on their Greek alphabet in most places, so I use a mnemonic, mean parentheses X and SD parentheses X, to mean the same thing. So it's a little easier to figure out what we're talking about. So mean parentheses X will be the mean of the distribution for X, also known as mu. SDX would be the standard deviation for the distribution of X, also known as sigma. Now, the definition for the mean of X is the integral over all X of X times f of X dx. When is the last time you evaluated an integral? These are not numbers you find in practice. These are concepts. This is the target that you're taking shots at when you compute on an average. Think of it that way. The variance for x is the integral over all x of x minus the mean quantity squared f of x dx. And the standard deviation is the square root of the variance. Simple enough. But you see, these are things that remain unknown in practice. So we use our statistics to estimate parameters. So the average and sometimes the median will be used to estimate the mean of the distribution for x. The adjusted range, r divided by d2, will estimate the standard deviation parameter. The adjusted standard deviation statistic, s divided by c4, estimates the standard deviation parameter, SD parentheses x. I didn't invent this mess, folks. I know we've got a standard deviation that's a parameter and a standard deviation that's a statistic. I will at least try to attach a label, or we'll use, if it's S, it's a statistic. If it's SD parentheses X, it's a parameter. And there's a glossary in the back of the textbook that says just that. And the adjusted root mean squared deviation, S sub n divided by C2, also estimates the standard deviation parameter. Sheesh. So the first distinction you need to make is between the statistics, the numbers we can get our hands on, and the parameters, the concepts, the quantity, the values we're trying to estimate. But it's a little more complex than this. So you're going to need to turn to page 24. Page 24. We'll need to fill in the blanks. So on the x-plane, we have a mean parameter that we're going to need to estimate. And the distribution for x also has a standard deviation parameter that we need to estimate. So I guess I should label this. This is the distribution of the individual values, x, the original data. So there are two parameters we're going to need to estimate. Then on the x bar plane, there is a mean. Mean of x bar. And there's a standard deviation for x bar. Two more parameters we're going to have to estimate. Now it turns out the mean of the distribution for x bar is equal to the mean for the distribution of x. They're twins. Always equal. And the standard deviation for the distribution of x bar is the standard deviation for the distribution for x divided by the square root of the subgroup size. N. So if I know the first two parameters, I know the second two. That's nice. Then down on the range plane, we've got the mean for the distribution of the ranges. And we got the standard deviation for the distribution of the ranges. Two more parameters we're going to have to estimate. Now the mean for the distribution of the ranges is equal to little d sub 2 times the standard deviation for the distribution for x. And the standard deviation for the distribution of the range is little d sub 3 times the standard deviation for the distribution for x. These equations are essentially the definition of D2 and D3. There's a lot of mathematics behind that, but that's the bottom line, the result. Now, this is all wonderful, except in practice, it's all unknown. We don't know any of these values. We know how they're related, and that's helpful. But we don't know how, we don't know the values for any of them. So how do we estimate these parameters? Well, that is what we'll figure out on page 25. On page 25, we'll go to work on estimating these parameters. And we'll start right in the middle of the page. We're going to estimate the mean of the distribution for x bar. What was the central line for the average chart? The central line on the average chart was the average of the averages, called the grand average. X double bar, wasn't it? I mean, this is almost intuitive. I want to estimate the mean of x bar. I use the average of the x bars to do it. Now see, I know average and mean are synonyms in English, but here in this class, an average is a statistic and a mean is a parameter. And I'll make that distinction clear. Well, now that I know that, how am I going to estimate the mean of the distribution for x? Well, I'm lazy. So I'm going to use x double bar here as well. Okay, let's go down here to the range chart. We need to estimate the mean of the distribution of the ranges. What statistic comes to mind? R bar. That's the central line on the range chart, isn't it? You want to estimate the mean of the ranges, you use the average of the ranges to do it. Duh. This makes sense. Now that we've taken care of location, let's go back up here and go to work on standard deviation. Let's go up here to estimate the standard deviation for the distribution of x. I want you to use the bottom equation on page 24 and the bottom equation on page 25 and figure out what we can use to estimate the standard deviation for X. We use R bar divided by D2. So that's a number we can compute. Now that we have that, let's work our way down the page. We want to estimate the standard deviation for the distribution of X bar. So given the relationships you see on the previous page between the standard deviation for X and the standard deviation for X bar, what do we use?
R bar over D2 divided by root n.
R bar over D2 divided by root n. Yes. Now we come down to the range. Estimated standard deviation for the ranges. Based on the relationships on the previous page, what can I use here?
R bar divided by D3 divided by root n.
We have D3 times R bar divided by D2, wouldn't we? So you see, Abhishek, here we've done 6 parameters and we've only used 2 statistics.
Okay, agreed.
That's one reason why you need to make a distinction, because it can get really confusing very fast. We've just estimated 6 parameters, 3 means and 3 standard deviations. And the way we use X double bar and R bar changes depending upon whether we're talking about the original data X, the subgroup averages X bar, or the subgroup ranges R. Once we have page 25, all we need is the part 3 of the empirical rule, and we can write our formulas for our 3 sigma limits. And we'll do that on page 26. So our central line for the distribution of X on the X plane, our central line will be X double bar or X bar, depending on which chart we're using. If we're using an average and range chart, we'll use X double bar. If we're using an XMR chart, we just use X bar itself. But the upper natural process limit is going to be X double bar plus 3 times R bar over D2. And the lower natural process limit will be X double bar minus 3 R bar over D2. For the averages, our central line is X double bar. The upper average limit would be X double bar plus 3 R bar divided by D2 square roots of n. And the lower average limit would be X double bar minus 3 r bar divided by d2 square roots of n. Now, the picture here has been drawn for subgroup size 5, and that's going to create an issue down here on the range chart we'll talk about in a second. So let's move on down to the range plane. Our central line is r bar. The upper range limit would be r bar plus 3 d3 r bar over d2. The lower range limit would be r bar minus 3 d3 r bar over d2. Now there are the formulas for your 3 sigma limits without the scaling factors being involved. If we factor out, well, down here on the range chart, we factor out the r bar, we've got 1 plus 3 little d3 over little d2. That's what we call capital D4, our scaling factor. And 1 minus 3 little d3 over little d2 is a scaling factor we call capital D3. But capital D3 is negative until your subgroup size is 7. So you hit the barrier of 0 and generally don't have a lower limit on the range chart until you have a larger subgroup size, 7 or more. If we work our way back up the page, take everything that's multiplied by r bar and isolate it. And on the average plane, that's called capital A2. That would be 3 over D2 square roots of n. That's your A2 scaling factor. And up on the chart for individual values on the x-plane, take everything multiplied by r bar. We call that capital E2. That's 3 divided by D2. Now these labels for these scaling factors are older than I am. They were cooked up in World War II. So I'll not try to change them. And obviously there's a bunch of them. And you can look in the glossary in the back of the textbook and see several of these and where to find their definition. We'll see that in a minute. So you can use the scaling factors, or you could use the formulas on page 26. And except for round off error, you're going to get the same values. Now, this whole scenario, page 24, 25, 26, is explained in the textbook, Understanding SPC, pages 236 to 248. So that's a reference to the textbook if you want to go over this again. And having done this, that makes the section in the textbook a little more understandable. This is instant pudding, folks. Add data, stir, instant limits. That's what the scaling factors are there for, to make it as simple as possible. But when you use those scaling factors, you are computing 3 sigma limits. Here you're computing 3 sigma limits on the x-plane. Here you're computing 3 sigma limits on the x-bar plane. Here you're computing 3 sigma limits on the range plane. The 3 is built in. It's automatic. So the scaling factors let you get 3 sigma limits.
SPC is fundamentally different from the techniques taught in courses in statistics. An appreciation of these differences can help to avoid all sorts of confusion. But first, Dr. Wheeler turns to page 215 of the Understanding SPC text to clarify when to use each type of process behavior chart.
We're going to talk about when to use an XMR chart. That question's already come up before the class started this morning. And so in Understanding SPC, I'd like to ask you to turn to page 215. You have 2 charts, the average and range chart and the XMR chart, available to you. It helps to make a distinction between regular chart data and periodically collected data. Regular chart data are data for which you may choose both the subgroup size and the subgroup frequency. This is, that is, the subgroup size is independent of the subgroup frequency. For such data, the average and range chart will generally be the best chart to use. The ability to choose the subgroup frequency will allow you to obtain subgroups at whatever frequency matches the frequency with the time period on which the time scale on which the process can change. And the ability to independently select your subgroup size will allow you to collect several observations in a short period of time and thereby use the increased sensitivity of the average chart. But periodically collected data are data for which each value has a time period attached. So the choice of subgroup size is not independent of the choice of subgroup frequency. Once you choose a subgroup size, you've locked in a subgroup frequency because there's an inherent time period attached to each number. In such case, the XMR chart tends to be the preferred chart. So, middle of page 216. Regular chart data may choose both subgroup size and subgroup frequency. Organize the data into rational subgroups. Now, rational subgrouping is a major topic for this afternoon. And use average and range charts. Periodically collected data, frequency for individual values is fixed. Choice of subgroup size determines subgroup frequency. Organize the data in a rational manner. Use an XMR chart. Now, an XMR chart is intended to be a comparison between apples to apples to apples, not apples and oranges and bananas and grapefruit. So you gotta have a sequence of values that are logically comparable when you use an XMR chart. That's what I mean, organized in a rational manner. Now, sometimes there's so many data, you want to compress the data down, and you can do that by using an average and range chart and get a historical summary, but you're going to lose the sensitivity of the individual value, showing you what's happening at a fine scale. So it's a judgment call here, but usually we want the XMR chart here and the average and range chart up there. So there's a guideline on when to use each chart. Let's now go on to how SPC differs from statistics. That's going to be page 249 in Understanding SPC. The difference between Shewhart's approach and the approach we use in all other areas of statistics can be summarized by how they approach the equation that defines the area P under a curve f of x between the 2 points A and B. So the integral from A to B of f of x dx equals the area P. Now, the statistical approach to this equation, we select a value for P that is close to 1, usually 95%. Once P is fixed, we pick an appropriate probability model, f of x. And with that model, we then solve the equation for A and B to find the critical values. And then we use those critical values in our analysis of the data. And so statistical inference uses customized values for A and B that result in a specified probability of a false alarm for a given probability model, f of x. And when you're thinking like that, the probability model is important, because if you change the probability model, you're going to change your value for P. Unlike statistical techniques, they're built on functions of the data, which tend to have known probability models. Shewhart was working with the original data themselves. And in this, he observed that we will never have enough information to fully specify the probability model for our original data. And if we cannot specify our probability model, then the approach used by the statistical approach outlined above breaks down. So Shewhart took a different approach. He decided to use generic fixed values for A and B, such that for any probability model f of x, the value of P will be close to 1. In practice, we don't really need to know what the value of P is. As long as it's reasonably close to 1, the values A and B will result in very few false alarms. In this regard, Shewhart found that symmetric 3 sigma limits provided a reasonable trade-off between getting false alarms and missing signals of economic importance. Or I should say, and finding signals of economic importance, whichever way you want to put it. Shewhart chose to use generic fixed width limits that work with all types of data, rather than customizing each analysis to maintain a fixed probability of getting a false alarm. So we can summarize the difference like this. The approaches are 180 degrees opposite. Statistics says fix P, find f of x, and let A and B vary. Shewhart says fix A and B so that for any f of x, P is close to 1. And that difference in approach is why some statisticians have trouble understanding Shewhart. I made a lot of these mistakes myself, but I made them where it didn't matter at the university, teaching the unconscious. After I taught the first class in SPC, and they handed me the book and said, here, teach this class. I said, I've never heard of that. They said, oh, it's easy stuff. Read the book, teach the class. I won't say much for the first class. After I taught the class, David Chambers, the co-author of the textbook, could tell by the way I talked, I really didn't understand it. So he said, now you've taught the class, go get Shewhart's book out of the library and read it. So I did. About a year later, he said, you need to read Shewhart again. He just kept throwing me back in it until I finally got through my thick head that this is different. And this is how it's different. So in an article in 1944, Shewhart wrote, page 250, classical statistics start with the assumption that a statistical universe exists, a probability model, whereas SPC starts with the assumption that a statistical universe does not exist. Measurements of phenomena in both social and natural science, for the most part, obey neither deterministic nor statistical laws until the assignable causes of variability have been found and removed. So, Shewhart's first book came out in 1931. E.S. Pearson got a hold of it, corresponded with the Shewhart, and then wrote his book in 1935, which became British Standard 600, the application of statistical methods to industrial standardization and quality control. And Pearson, a well-known name in statistics, was thinking like a statistician. So he said, you really need 3.09 sigma limits, and you need a normal distribution. You see, he's coming at it from the statistics side. And when you come at it from the statistics side, you've got to have an f of x. You can't do the statistical approach without a probability model to stick into that integral equation. And Shewhart wrote a rebuttal, came out in 39, edited by Deming. And he tweaked Pearson by just tweaking his title. It's not statistical methods in search of an application. It's statistical method from the viewpoint of quality control. How to use statistics to take action. So this tension has been around. And so the academic version of SPC follows Pearson. And the applied version of SPC follows Shewhart. So there have been two strands, and have been there since 1935. I was on a panel discussion in 2000 on these two different strands. I put that slide up, and all of the panel agreed, yeah, that's where it started, right there. Now let's go to page 22 in the workbook. So we've been talking about statistics and parameters. Now, here is the upshot of that. If you don't make this distinction, and if you're going in there like the statistics approach, you're not going to make this distinction. When the underlying process is not changing over time, we can collect observations from the process. We can use those observations to compute summary statistics, such as the grand average and the average range. Then we can use those summary statistics to calculate limits that describe how a predictable process should behave. And if our data are consistent with our predictions, we can say our process is reasonably predictable, and we can use these same statistics to estimate process parameters, such as the process average, the process standard deviation, the process capability, etc. But if our process is unpredictable, It's changing over time. Again, we can collect data from the process. And since statistics are nothing but data plus arithmetic, there's nothing to keep us from computing our summary statistics, the grand average and the average range. And we use these summary statistics to describe how data from a predictable process ought to behave. But here we see that the data don't fit with that prediction. So we don't have a predictable process. That means we don't have a process average. We don't have a process standard deviation. We don't have a process capability because they're all constantly changing. So any attempt to use the statistics to estimate process parameters is just meaningless. And that's why we need to make a distinction between statistics and parameters. And we need to understand that Shewhart's argument is not built on estimating the parameters and estimating the p-value. It's a one-size-fits-all approach that allows us to characterize the process as being predictable or unpredictable. So we can take action to find the assignable cause in this case, and we can avoid taking action to look for assignable causes in the other case.
I would now like to go over the 4 questions in statistics. You will find this material on page 72 and 73 in your SPC workbook. There are 4 questions in statistics. The first of these is description. Given a collection of data, we can characterize the various properties of the data using a few numerical summaries, things you're familiar with, like the average, the range, the standard deviation statistic, a proportion, and so on. The second question in statistics is probability. Given a known population, describe the properties of random samples drawn from this population. For example, the bead bowl here might have 4,000 white beads and 1,000 red beads. The probability of getting 5 red beads in a sample of 50 beads is said to be 3%. That's probability theory, figuring out the probability of various sample outcomes. The third question in statistics is inference. Given a population with an unknown composition, and given a sample obtained from this population, we use the properties of the sample to infer characteristics of the population. So a sample that consists of 45 white beads and 5 red beads, we would say is consistent with a population having anywhere from 4 to 22% red beads. That's the confidence interval for our sample result. Now, description, probability, and inference are the 3 main topics you will find in most introductory textbooks in statistics. But the 4th question in statistics is homogeneity. Given a collection of outcomes, did these outcomes come from one population, or do they contain information that suggests they might have come from several different populations? And this is what we've been talking about and will be talking about throughout this class. You see, descriptive statistics assume that data come from a single universe. Probability theory assumes the data come from a single universe. Statistical inference assumes the data represent a sample from a single universe. When your data come from multiple universes, descriptive statistics fail probability theory fails, and statistical inference becomes meaningless. So scientists, engineers, and everyone else who attempts to analyze data must begin with the question of homogeneity. Are the data homogeneous? If the answer is yes, then we can use statistical inference to estimate the process parameters, and then we can use probability theory to make probabilistic predictions. But if the answer is no to the question of homogeneity, you need to find out why the data are not homogeneous and fix the process. Collect more data, go back to the top. The question of homogeneity trumps all other questions. The question of homogeneity trumps questions about which probability model to use. It trumps questions about how to torture your data with transformations. It trumps questions about which alpha level to use. In truth, you cannot define an alpha level. You cannot fit a probability model, and you cannot hope that your statistical inferences will work as advertised if you do not have a homogeneous set of data. You see, the secret foundation of statistics is assume your data are homogeneous. If you read articles in statistics, right at the first paragraph or two, you'll see a statement about we assume we have a collection of random variables that are independent and identically distributed. And that independent and identically distributed phrase is equivalent to assume your data are homogeneous. So if your data are not homogeneous, it is the height of wishful thinking to imagine that either simple or sophisticated mathematical computations are going to produce anything other than nonsense. And the secret of data analysis is that your data are rarely homogeneous. Mere computations cannot cure a lack of homogeneity.